Hello, everyone. So this is the first video post test 2, where we really get to study applications of the exponential function and eventually the logarithm function as well. We now begin to study processes that require that involve exponential growth or exponential decay. And I kind of hinted at this very, very early on in the discussion about exponentials, I guess 2 weeks before the test, but now we kind of dive into it in much more detail. So here's the basic setting for this. Oh, Kat is here. You were napping. Go nap again. Okay. In many processes, the rate of change of the quantity of interest sorry. Is proportional to the quantity present at a given time. So this quantity can be all kinds. I mean, I'm being very abstract here, but this can refer to all kinds of different things, right? So, for example, if y of t is equal to the amount of bacteria in a cell culture at time t, then the rate of change of the bacteria, right, of the growth rate of the bacteria, oops, let me clean this up a bit, is equal to k, is some constant, times the amount of bacteria present. Is growing is a multiple of the amount of bacteria present at the given time t. And this makes sense if we think about it, because like I was saying at the very beginning of our discussion of exponential functions, right? You have some bacteria, and each bacteria can divide into 2 other bacteria, right? Each bacterium can divide into 2 other bacteria. So the rate at which the bacteria is growing is proportional at any given moment to the amount of bacteria you have, like in your bacteria dish, petri dish, wherever it's growing. So that's an example where, so this k is a constant, where the derivative or the rate of change is proportional to the amount of stuff that you would have. But this is, I mean, there are also other examples, and the other example that's kind of a classical example is not about growth, but is about decay. So radioactive decay is another one of these situations. So this is well, this may be kind of harder to visualize, but the amount, the rate at which a radioactive isotope decays is proportional to the amount of isotope at a given time t. So when they talk about like the Chernobyl disaster or the Fukushima disaster that happened about a decade ago, they say, okay, such and such a thing has a half-life, such a radioactive element has a half-life of, say, 60 years or 90 years. And that means that it will take, say, 90 years for the amount present to decay to half that amount. And a long half-life, like 90 years or 60 years even, is really, really bad, because that means that element, that radioactive element, is going to be present in the environment for a long time and emit radiation that's harmful to the environment and to anything in the environment, to us, to animals, to the flora and fauna. So I think in Fukushima they were concerned with thorium, a certain isotope of thorium, I can't remember, which had like, I think, a half-life of, I keep saying 60, but I think 90 years, and that's very, very dangerous to have that in the environment. So here's another this is another situation where you have a rate of change that is proportional to the amount of the substance at a given time. So a radioactive isotope decays at a rate proportional to the amount of isotope present at a given time t. Present in the environment at a given time t. So again, we have, if y of t is the amount of radioactive isotope or radioactive substance, present in the environment at time t, at a time t, we have y prime of t is again proportional, so it's a multiple of the amount of the isotope present. So the derivative is a multiple of the amount, or proportional means it's a multiple of the amount present at the time t. So, and there are applications to finance as well, but those are a little harder to explain, so I'll get to that. I'll get to that in the next video. But I mean, the idea of the applications to finance is, if you have an investment account that's earning interest that's kind of compounded indefinitely, then the amount of money you're gaining is proportional to the amount of money you have present at time t. It's a little bit more tricky of a model, but it's the same idea as the first case of the bacteria. It's exponential growth. But let me kind of bring these two examples together and tell you what they have in common and tell you what they have differently, and how we're going to study them. So we have, I should have given this a name. So this is bacterial growth. And that was reactive decay. So in both of the examples, bacterial growth and radioactive decay, the function y of t satisfies the differential equation y prime of t equals k times y of t for some constant k. Okay, so this word differential equation is kind of a fancy way of saying an equation that involves a derivative of a function and the function itself. That's it. I mean, there are more general notions of this, but we won't get into it in this class. Okay, so it's just an equation that involves a function and its derivative. So this is the equation, this is the derivative, is k times the function. That's it, right? So like in layman's terms, if you like, so the derivative of y, the derivative of the function is k times the function. That's all it's saying. Okay. Now, this differential equation, like it appears in these applications. Like I said, it also has something to do with interest. And way back in the beginning of the discussion of exponentials, I mentioned that air resistance for like motion in free fall also has a differential, has a differential equation like this, where the rate of change of the speed of the object is proportional to the speed of the object. Because if you think about air resistance, the faster you're going, the more resistance you'd have. So this appears so much in nature in all kinds of places, physics, finance, biology, chemistry, that this is why the exponential function is so important. Because the exponential function is essentially the only solution to this differential equation. This differential equation has the unique solution that y of t equals some constant c e to the kt, where c is a constant. And this e here, this is our friend, the natural exponential function, but it's a natural exponential function evaluated at k times t. What does it mean that this function is a solution? Right? So what does it mean? What does it mean when I say this is a solution of the equation? It means that if we have a function y of t which satisfies the equation such that y prime of t equals k times y of t, then y of t has to be equal to c e to the kt. So if you have a function whose derivative is k times the function itself, then y of t must be equal to c times e to the kt for some c. And conversely, if y of t is equal to c to the ekt, then y prime of t equals k times y of t. So that's what it means to be a solution to this equation. It means that if you have a function y that satisfies this equation, it has to have this form. It has to be some capital C, some constant, times this exponential function. And this k, this k is part of the equation data, so that's baked in. There's no ambiguity there. And conversely, it means that if the function is this c times e to the kt, it satisfies this equation. So and that is the unique, up to this ambiguity with capital C, which we'll discuss in a moment, that is the unique solution to this equation, to this differential equation. And that's, because this differential equation occurs in so many places in nature, this is why the exponential is so dang important for us in math and sciences and finance and all kinds of stuff. So let me kind of give this its own little place box. Okay, so sorry about that. So we can actually check this statement. So I can't show you. So I can't show you that if a function satisfies this equation, it has to be of this form. That requires a lot more tricky math that you don't do until like differential equations, which is the fourth thing in the normal calculus sequence. It's not terribly hard, but it requires like more stuff. But I can show you that if we start with this exponential, the derivative, its derivative satisfies this equation. That its derivative is proportional to the function itself. And this shouldn't be a surprise from what we've done already in with exponentials in this class. So let's suppose that y of t equals c e to the kt, and show it is a solution to the differential equation. Y prime of t equals k times y of t. Okay, so we need to compute y prime. Y prime of t is the time derivative of c e to the kt. C is a constant, so we can pull it out of the derivative. And this is e to the kt. And now, hopefully you remember this function here, right? I'll just write this in gray. So e to the kt is the composition of two functions, is f composed with g of t, where the external function is our friend, the natural exponential, and the internal function is this linear function k times t. K is a constant, right? K is a number. And then we had a formula for this before the test that said that the derivative in this case from the chain rule was just e to the kt times the derivative. Oh, sorry, I should write out the function on the left-hand side as well. The derivative of e to the kt is e to the kt times the derivative of k times t, and that's just k. So it's just k e to the kt. So that's from our formula from before test 2. And so this is just c k e to the kt, and we can just bring the k out like this, right? And write it as k, k and c are numbers, so the order of which you multiply them doesn't matter. And so you get k y of t, and that's what we wanted to show, that the derivative of this guy, where did it go? The derivative of this fellow, right, is equal to k times the function, k times itself. Okay, so like I said, I can't show you that any function that satisfies this differential equation has to be an exponential, but certainly an exponential works, and we'll go with that for now. All right. So there are two kind of broadly speaking cases to consider for these exponential functions of this form c e to the kt. And the two cases mirror the two examples that I did for you a moment ago. So there are, broadly speaking, two cases to consider when studying the functions y of t equals c e to the kt. And so, it depends depending on whether the function is increasing or decreasing. Okay, so you have this equation y prime of t equals k times y of t. So if in one case if k is positive, right, that means that this quantity y is growing at an amount proportional to the amount present at a given time t. That's like the bacteria situation. So this is exponential growth. And this k is called the growth constant, not the gross constant, the growth constant. The other situation is the radioactive situation, where the amount of the quantity is decreasing where the quantity is decreasing in an amount proportional to the quantity present. So that's like radioactive decay, where the isotope is decaying at a rate proportional to the amount present at a given time t. So this is called exponential decay. And K is called the decay constant in this case. I'm running out of room. Okay, so sorry about that. And so then in both situations, right? So in this situation, we can kind of maybe clean this up a bit. And what I can do, I'll clean it up a bit for you here. It will spill onto a different page, but that's okay. So kind of divide this situation. So in the growth case, K is positive, K is called the growth constant. And the K is negative, is exponential decay. So then K is decay constant. And so in both cases, we have this function, right? The quantity y is an exponential function c e to the kt. And I want to talk a little bit about what this capital C is. So if you plug in 0 to this, in either case, if you plug in 0, you get c e to the 0 times k, which is c e to the 0. And if you remember, any of the 0 is 1, so that's just c. So we have a nice interpretation of this constant capital C, right? It is the initial amount of quantity present. So capital C is the initial amount of quantity present, amount of substance present. So whether it's bacterial or radioactive material. So it's the initial quantity of substance present, or initial amount at time t equals 0. So in the bacteria case, this would be like y of c is the initial amount of bacteria present. And in the radioactive case, this would be the initial amount of radioactive material present, radioactive isotope present. Okay, so I think I've done enough mumbo jumbo talking about this in general. Now we have hopefully enough kind of background material and context to do some nice examples. So let's do that. Okay, so examples. So the first example, you wouldn't be surprised, is about cell culture. Okay, so maybe it's not bacteria, but this is some cells. But it's a similar idea, exponential growth. Okay, so after t hours, there are p of t cells present in a culture where p of t is equal to 5,000 e to the 0.2 t. 0.2 t. Okay, we have to answer the following questions about this. I'll do one at a time. How many cells were present in the culture initially? Now, we could kind of recognize the form of the function, or we could just plug in 0. Either works, but maybe the easy thing is to plug in 0, or it depends how comfortable you are with what I just said above. But P of 0, right, that'll be the amount of cells present at time 0. So we plug in 0, we get, okay, so P of 0 is 5,000 e to the 0. E to the 0 is just 1. So it's 5,000 times 1, so it's just 5,000 cells are present at time t. So 5,000 cells are present at time t equals 0. Okay, now give a differential equation satisfied by the function p of t. Okay, so where's our p of t? There it is. Let me grab it for us. Oh, that backfired. I'll just rewrite it down here. Okay, so we recognize that p of t is of the form p of t equals c e to the kt, where capital C is 5,000 and our little k, the growth constant, is 0.2. So this is an exponential growth function. So from what we did above, we know that p of t satisfies the differential equation p prime of t equals k times p of t, and this is just 0.2 times p of t. That's it. So we have an exponential growth function with growth constant k equals 0.2, so it satisfies the differential equation that the derivative is the growth constant little k times p. Okay, so now that's kind of boring stuff. Let's do some, actually use this function to understand what's happening with the cell culture. So one thing, so this is, I guess this is C now, I'm gonna call it 3, but call it C, part C. One thing that's a very common thing you want to do when you're studying exponential growth is you want to understand how long does it take for the quantity to double. Like, say you start off with, this case, we start off with 5,000 cells. How long is it going to take until we get 10,000 cells? So when will the initial quantity of cells, or how long, let me phrase it this way. How long will it take for the initial quantity of cells to double in size? Okay, so we saw in part A that we started off with 5,000 cells. So we want to find the time t at which we will have 10,000 cells. So this amounts to solving, oops, sorry, the pen's getting weird. To solving the equation 10,000 equals p of t for time t. But this is actually just an exponential equation. So if we write out, because 5,000 then equals, 10,000 equals 5,000 times e to the 0.2 t, and we want to solve for t. This is a problem we've already done. It's not even involving, it doesn't even involve calculus. It's just a problem of solving exponential equations. So we just need to solve this exponential equation for t. Okay, so we know how to do that. We isolate the exponential on one side. So I'll put this in parentheses. On one side, and then take the natural logarithm of both sides. So we get, so if we isolate the exponential, we get 10,000 divided by 5,000 is 2 e to the 0.2t. Then you would take the logarithm, natural, of both sides. And of course, the logarithm of e to the 0.2t is 0.2t. That's the whole beauty of the logarithm. So you get the logarithm of 2 is equal to 0.2t. And so you get that ln2 divided by 0.2 is t. And this is approximately, if you punch it out in your calculator, 3.5 hours. So it takes about 3.5 hours for the culture to double. To double in size from the initial amount. Okay, let's do an, so this is the kind of game you can play, and it just amounts to really solving exponential equations. There was no calculus in that point. Let's get back to some calculus for a moment with part D. At what rate will the population of cells be increasing when there are 100,000 cells present? Question mark. Okay, well, this you have to think a little bit more carefully about, because you can make this, I mean, there's different ways to do this, but you could make this much harder than need be. So the easiest way to do this, the easiest way to figure this out is to remember that the function p of t satisfies the differential equation that p prime of t equals 0.2p of t, which we found in part B, the second part of the question. Okay, and so now we just want to find, what we're asked to find the rate at which the cells are increasing when the P of t is 100,000. So now we can just take 100,000 and plug it in to the right-hand side of the equation and get what the derivative is at that time when there are 100,000 cells. If you don't do this, if you don't use the differential equation, then you got to find the time at which there are 100,000 cells, and then you got to plug that time in. You got to find a derivative formula and plug into the derivative. There's many more steps. But if you go back and remember the fundamental differential equation that started the whole story, it's easy to find the derivative at any when you know the amount of quantity present, because this whole process is working the way it does because the derivative is 0.2 times the amount of quantity present at a given time, the amount of cells present. So we just plug P of t equals 100,000. The pen is acting very weird. Into the right-hand side, RHS, of the above differential equation. Into the above differential equation. So when we do that, we get P prime of t equals 0.2, times 100,000, and 0.2 is 1/5, so it's 1/5 of 100,000, which is 20,000. And we should have units cells per hour. So when there are 100,000 cells present, the cells are growing at a rate of 20,000 cells per hour. So that's what that means. So i.e., rate of 20,000 cells per hour. Okay, so that's all I want to do about biological growth for a moment. Let's do a decay example now, okay? But we see kind of what we can, see what we can do with decay. Okay, so decay problems tend to be phrased a little differently because in chemistry, like I was saying, in radiochemistry and physics, it's natural to talk about the half-life of an isotope. So the information you're usually given is the half-life. And the half-life is the time it takes for the amount present to decay to half that amount. And from that, you need to figure out things about the function. So that's the game. Okay, so here's how it kind of goes. So radioactive cobalt cobalt 60 has a half-life of 5.3 years. So that's a pretty short half-life. So this is not so dangerous. Find the decay constant. Okay, so what do we know? So we know that it takes 5.3 years for the cobalt 60 to decay to half initial amount. And we know that, as I talked about earlier, the radioactive elements satisfy exponential decay. And we know that if A of t is the amount of cobalt present, at a time t, then A of t is given by the initial amount, which we'll call A of 0, e to the kt, is an exponential decay function. Now, okay, so that's just from the setting of exponential decay, but now I need to translate this business that takes 5.3 years for the cobalt 60 to decay to half the initial amount. I need to translate that information into an equation. That's actually not too bad to do. So we're told that A of 5.3, if we plug in 5.3 years, half the amount is present, right? Half the initial amount is present after one half-life of 5.3 years. So we can use this to set up an equation. Half A0 equals E times 5.3, 5.3K. Oh, A0 is here, 2. And we can solve this equation for K. And that's how you do it. Solve this exponential equation. For the decay constant, K. Okay, so that's pretty easy. So let's see what we get. So if we have 1/2 A0 equals A0 e to the 5.3K, you can cancel, switches between the eraser and the pen a lot. Cancel off the A0s, the initial amounts, and you get 1/2 equals e to the 5.3K. And now you can take the logarithm of both sides, and you get the logarithm of 1/2 is the logarithm of e to the 5.3K. And so then using the property of the logarithm, canceling out the exponential, you get 5.3K is the logarithm of 1/2. And so you get K is equal to the logarithm of 1/2 over 5.3. And I guess I should punch this into a calculator. This is approximately minus 0.13. And note it's negative as it should be because we're dealing with exponential decay. Okay, so that's the kind of thing you do with a half-life problem. It's pretty standard stuff. Let's do another type of growth problem, and then we'll call it a day for this video. And I'll talk about compound interest in a second video, but it won't be a full 50 minutes worth. And then there's a third topic which has to do with logarithms, and we'll get to that later. Okay, the third example. The rate at which the number of cells changes is proportional to the amount to the number of cells present at a given time. Proportional. At a given time t. So that should tell you a rate of change of number of cells present is proportional. Sorry, rate of change of number of cells is proportional to the amount of cells present at a given time t. This is exactly the situation we began with at the beginning of the lecture. This is exponential growth. Okay, so keep that in mind. That's what that's saying. In 6 hours, an initial population of 1 million cells grew to 9 million. How many cells are present 15 hours after the population of 1 million cells? Clean this up. was initially observed. Okay, so there's a lot. This is more complicated than the last couple of questions because, I mean, the last several ones, especially the first one on the bacterial growth or cell growth, kind of led you by the hand step by step. This, you have to kind of do everything at once in some sense and unravel everything at once. Okay, so since we are told, so let me say, okay, so let me start defining a function. So here's the solution. Let P of t be the population of cells, number of cells present, in millions, because I don't want to write all these zeros. So this is going to be the number of cells present in millions, t hours after the initial population of 1 million cells was observed. Okay, now since the derivative, right, of p is proportional to p of t, we know that p of t has to be an exponential growth function. Right? So the amount of cells is increasing at a rate proportional to the amount present. We are told that in the problem. So P of t has to satisfy this differential equation, which means from our earlier discussion that it's an exponential growth function. Right? Okay, so now C, P of 0, we're told when we start looking at the cells is 1 million. So this means the initial amount present is 1 million. So we can put that into our function, makes it easier. But we don't, and we want to find, and now we want to find how many cells there are 15 hours later, right? So what does that equal? Now, the tricky thing here is we don't know the K, right? We can't do this directly. Do this right away, or we can't compute this. Because we don't know the growth constant K. Right? But there's some information in the problem that helps us find it. So we go back to the problem. And what we're told in the problem is that in 6 hours, the initial population of 1 million cells grew to 9 million. So that says that P of 6, this population 6 hours after, is actually equal to 9. And that gives us an exponential equation that we can solve for the growth constant K and then use to compute P of 15. So this is often how these problems work. You're giving some information about the initial amount. You want to find the amount sometime later. You don't know the amount at that time later, in this case 15 hours, but you know it in some intermediate time, and that allows you to find the growth constant. But we are told in the problem that P of 6 is equal to 9. And that's the same thing as saying that E to the 6K is equal to 9. And this is an exponential equation that we can solve for K. for a little k. So let me clean this up. This is supposed to be a k. So we get the logarithm of 9 is 6k. So k equals the logarithm of 9 over 6. And that means that p of t, and it's kind of good in this situation not to, I mean, you'll get a better answer if you don't simplify. Sorry. Stupid thing. You'll get a better answer in the end if you don't simplify the k in your calculator yet. You'll introduce less errors, but at the end you should. And so p of 15 you can compute is E is equal to e to the ln 9 over 6 times 15. And if you punch this out on your calculator, you get approximately 243. So 15 hours after we start observing the culture, there are 243 million cells present. That's the story. Okay, so I think these are fun problems. I think it's cool to see the applications of some of these exponential functions and the fact that they occur ubiquitously all over in science, and we'll see financial applications in a bit, and also social sciences as well. You can talk about populations and demographics and things like this. Also using exponentials, that gets a bit more complicated because you have to worry about other things in your models, such as resources and so forth. And we won't get into that, but this is a starting point for all this stuff. So thanks for tuning in. I hope you enjoyed exponential decay and growth, and we'll do interest in the next video.